Hello, in this lecture we'll answer two questions. In the first question, we find out the area of this rectangle ABCD, and in the second question, we find out the area of this gray shape with an inside square ABCD. So we'll start with the first question. In the drawing, we have rectangle ABCD, and inside this rectangle, we have this semicircle. In addition, you know that this is called AP. This is equals to 6 units units left. This is nice segment CP. That's equals to 5 units units left. Again, our mission is to find out the area of this rectangle ABCD. So first of all, ABCD is a rectangle, so all those four angles inside the rectangle ABCD are right angles. So this is a right angle. This is also a right angle. This is a right angle, and finally this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. And finally, we define the point of tendency of tangent DC with this semicircle. This point is point M. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. That is equals to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle. That is equals to x. We join points O and M together by straight line. OM is of course the radius of this semicircle, that is equals to x, and because of the fact that the radius OM that is equals to x, the radius OM is drawn to point M, that is the point of tendency DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do the quadrilateral DMOA. Inside this quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total the must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DMOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle plus a square. So, related to this quadrilateral DMOA is rectangle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, side MO must be equal to the opposite side DA, but MO is x, therefore the opposite side DA must be also equal to x units in its length. The opposite sides of the big rectangle ABCD must be also equal to each other. This is to say, in rectangle ABCD, side DA must be equal to the opposite side BC, but DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points P and E together by a straight line. By joining points P and E, you cannot create an angle APE. This is peripheral angle APE, and peripheral angle APE subtends on AE, that is the diameter of the semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So if we speak of rule 7, according to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the moment, we have a circle AB, the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of the circle, and therefore this peripheral angle ACB is equal to 90 degrees in its size according to this rule 7. So any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. And because of the fact that this is peripheral angle APE that subtends on AE, that is the diameter of the semicircle, it must be equal to 90 degrees in its size according to rule 7. In the next step, we define this angle as alpha. So in the right angle APE, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we will prove that the big right triangle ABC is similar to this small right triangle APE. So I write it down. We prove that the big right triangle ABC similar to the small right triangle APE. So why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the small right triangle APE, and angle A also belongs to the big right triangle ABC. So you can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle A, it is belong to the big right triangle ABC, it will be defined as angle BAC. And angle A equals to itself. So if we relate to angle A as it is belongs to the small right triangle EPA, it will be defined as angle EAP. Note it again. This equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So this is angle ABC. You write the big triangle ABC. And it is equal to this angle, that is actually angle APE. The small right triangle APE. Repeat again. Angle ABC in the big right triangle ABC equals to angle APE in the small right triangle APE. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees from alpha, therefore they are equal to each other. So actually, this is angle ACB. The right big triangle ABC, and it is equal to this angle. This is actually angle AEP. The small right triangle AEP. So repeat again. Angle ACB in the big right triangle ABC equals to angle AEP. The small right triangle AEP, they are both equal to 90 degrees from alpha, therefore they are equal to each other. So if we found out that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of this right triangle APA, therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle ABC is similar, this is the sign of similar to the right small triangle APE. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, you will derive that the following relationship exists between their sides. We derive that side AP of the small right triangle AEP over side AB of the big right triangle ABC is equal to side AE of the small right triangle AEP over side AC of the big right triangle ABC. Repeat again. We derive that side AP of the small right triangle AP equals side AP of the small right triangle AEP over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. AP equals to 6 units in itself according to what is given in the question over AB. AB is the missing side, so limit as it is. And it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x over AC. AC in total equals to 6 plus 5, that is 11. So in total, we should find out that 6 over AB equals to 2x over 11. Here we will first multiply this equation. And we get that 6 times 11 is 66, and it is equal to 2x times AB. Here we divide this equation by 2, and finally we get that 66 over 2 is 33, and it is equal to 2x over 2 is x. So in total, this expression equals to x times AB. So here we divide this equation by x, and finally we get that AB equals to 33 over x units in its name. This is side AB is equals to 33 over x units in its name. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABC times the width. The length of this rectangle ABCD is AB, and the width is CB. So in total, we should find out the area of rectangle ABCD equals to AB times CB. AB is 33 over x, and CB is x. CB is x. So in total, we should find out that the area of rectangle ABCD equals to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So the area of rectangle ABCD is equal to 33 square units. That is the answer to the question. So we finish with the first question. In the next step, I present to you the second question. We solve the second question of this lecture. Our mission in this second question is to find out the area of this grain shape. So in the drawing, we have square ABCD. In addition, we know that this is line segment VP is equals to this line segment PC. And we also know that this is triangle OPC. The side of this triangle OPC is 5 square units. Again, our mission is to find out the area of this grain shape. So we define the length of this line segment BP as A. BP equals to PC. So if BP is A, therefore PC must be also equal to A, because they are equal to each other. BC total equals to A plus A, that is 2A. And you know that all the sides of a square are equal to each other. Therefore, AD must be, side AD of square ABCD must be also equal to 2 units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the side of this angle as beta, then the side of this angle must be also equal to beta because they are equal to each other. We know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to side BC. those two angles are defined as alternating angles and are located between the parallels AD and BC. That is to say, AD is parallel to BC. Therefore, those two alternating angles that are located between the parallels AD and BC must be equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to rule 15. According to rule 15, alternating angles between parallels are equal to each other. Likewise, those two angles are also defined as alternating angles and are located between the same parallels AD and BC. This is to say, AD is parallel to BC. Therefore, those two angles must be equal to each other in their sizes because according to rule 15. So if the size of this angle is beta, if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to rule 15. So if we found out that those two triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to theta, those two angles are both equal to beta, and those two angles are both equal to alpha. So I write it down. If we found out that the big triangle ADO is similar, this is the sign of similar, to the small triangle POC, according to angle similarity rule. So in the next step, I'll present to you a new rule that relates to similar triangles, and we will implement the new rule in our drawing on those two similar triangles. The new rule is rule 22. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. Again, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two triangles, triangle ABC and triangle DEF, that are similar to each other. So according to this rule 22, the ratio between the areas of those two triangles, that is to say, the area of triangle ABC over the area of triangle ADF, that ratio is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of their corresponding sides? Here, side AC of triangle ABC is corresponding sides of side DE of triangle DF. Likewise, side AB is the corresponding side of side DF, and side CB is the corresponding side of side EF. So the square of the ratio of the corresponding sides, here side AC is the corresponding side of side DF. So the square of the ratio of those two corresponding sides is of course AC over DE squared. So in total, the square of the ratio of their area, the ratio of their areas, that is the area of triangle ABC over triangle EDF, is equal to the square of the ratio of their corresponding side. That is to say, it is AC square over DE square. Likewise, AB is the corresponding side of DF. So the square of the ratio of those two corresponding sides is AB over DF squared. And finally, CB is the corresponding side of side EF, and the square of the ratio of those two corresponding sides is CB over EF squared. Okay, so the ratio of the ratio between the areas of those two similar triangles is the area of triangle ABC over the area of triangle EDF, and that ratio equals to the ratio of the square of the ratio of their corresponding sides. So we can implement rule 22 in our drawing. Why? Because in our drawing we have already found out that the big triangle DOA is similar to the small triangle COP. So according to rule 22, the ratio between the areas of those two similar triangles, it is actually the area of triangle ADO over the area of triangle COP. That ratio, the area of the big triangle DOA over the area of the small triangle COP, this is the ratio between the areas of those two similar triangles, and that ratio equals to the square of the ratio of their corresponding sides. Side AD in triangle ADO is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of angle theta, and here side PC in triangle POC is also in front of angle theta. So side AD is the corresponding side of side PC. And the square of the ratio of those two corresponding sides is of course AD over PC squared. AD over PC squared. So this equation is the implementation of rule 22 on those two similar triangles DOA and POC. Okay. The area of triangle DOA is unknown, so we leave it as it is. Over the area of triangle COP, this triangle COP is 5 square units, so we substitute the area of triangle COP by 5, and it is equal to AD over PC. AD is 2A and PC is A. Again, AD is 2A and PC is A. Squared. Okay. So here we have A in the numerator and A in the denominator, so A we can cancel, and we left only with 2 squared, that is 4. So today we found out that the big triangle DOA over 5 equals to 4. Here we multiply the equation by 5, and you get that the area of the big triangle DOA is equal to 5 times 4, that is 20 square units. So if we found out that the area of this big triangle DOA is equal to 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of triangle ADO over side PC of the small triangle POC is equal to side AO of triangle ADO over side OC of triangle POC. Okay, again, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle AOD over side PC of the small triangle POC is equal to side AO of the big right triangle AOD or side OC of the small right triangle POC. AD is 2A over PC, PC is A, and this is equal to AO over OC. So here we have A in the numerator and A in the denominator, so A will get cancelled. So if we found out that AO times OC equals to 2, here we multiply this equation by OC, and we get that 2 times OC equals to AO. And again, if we found out that 2 times OC equals to AO. So we define the length of side OC as B. So we substitute OC by B in this equation, and we get that AO equals to 2B. So if we found out that if the length of this line segment OC is B, then the length of line segment AO is 2B. That is to say, AO is twice as long as OC. Okay. So in the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 23. Rule 23 is true in any triangle, so triangle ABC could be any triangle. So in this triangle ABC, if we draw the red line segment AP, it will divide triangle ABC into 2 smaller triangles. The first triangle is triangle ABP, and the second triangle is triangle APC. Rule 23 talks about the 2 small triangles that will be created by drawing red line AP and triangle ABC. According to this rule, rule 23, the ratio between the areas of those 2 small triangles is equal to the ratio between their bases. The base of this triangle ABP is BP, and the base of this triangle APC is PC. So the ratio between the areas of those 2 small triangles equals to BP over PC. That is the ratio between their corresponding bases. So in detail, the area of triangle ABP equals to the base BP times the height that is edge over 2. Okay, again, the area of triangle ABP equals to the base BP times the height edge over 2. Likewise, the area of this triangle APC equals to the base PC times the height that is edge. Both triangles have the same height that is edge over 2. So the area of triangle ACP equals to the base CP times the height that is edge over 2. So the ratio between the areas of those 2 triangles is equal to the ratio between those 2 expressions. And the ratio between those 2 expressions, we have here 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. Likewise, we have edge in the numerator and edge in the denominator, so edge also will get cancelled. And we left only BP over CP. So we cancel those 2 expressions, we left only BP over CP. So in total, we found out that the ratio between the areas of those 2 triangles is equal to the ratio between their corresponding bases. That is to say, it is BP over PC. So can I actually implement rule 23 in our drawing? Why? Because in our drawing, we have the big right triangle ADC. This big right triangle ADC has been divided by line segment OD. Again, the big right triangle ADC is divided by line segment OD. So all the requirements of Rule 23 are satisfied, and therefore we can implement Rule 23. According to Rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The base of triangle ADO is AO, and the base of triangle ODC is OC. So it is AO or OC. Repeat again. The ratio between the areas of those two small triangles is the round triangle ADO or the area of this triangle ODC. Then that is the ratio between the areas of the small triangles, and that ratio equals to the ratio between their corresponding bases. The base of this triangle ADO is AO, and the base of this triangle ODC is OC. So it is AO over OC. So this equation is the implementation of Rule 23 in our drawing. Actually, in the right triangle ADC. The area of triangle ADO is 20 square units. Over there of triangle DOC, the area of triangle DOC is unknown, so we leave it as it is. And it is equal to AO over OC. So actually 20 over the area of triangle DOC is equal to AO over OC. AO is 2B, and OC is B. So we have B in the numerator and B in the numerator, so B is cancelled, and we have to leave 2. So in total we found out that 20 over the outside DOC equals to 2. So here we multiply this equation by the outside DOC, and we get that 20 equals to 2 times the outside DOC. Here we divide this equation by 2, finally get that the outside DOC is equal to 20 over 2, that is 10. So if we found out that the area of this triangle DOC is equal to 10 square units. So as you know, the area of this triangle DOC is 10 square units. This is the right triangle ABC. The right triangle ABC can went to this right triangle ADC according to side rule. So all those two right triangles can go into each other. First of all, because of the fact that ABCD is a square, all of its sides are equal to each other. So all those two right triangles can go into each other. First of all, side AB or triangle ABC equals to side DC. for triangle ABC because ABCD is a square. In addition, side BC of triangle ABC equals to side AD of triangle ABC for the same reason. And finally, side AC is a common side that belongs to both triangles, so you can line out that side AC equals to itself is a common side that belongs to both triangles. So in total, if we found out that triangle ABC can go to triangle ADC according to side rule. So I write it down. Right triangle ABC congruent. This is the sign of congruent to the right triangle ADC. According to side rule. And from the fact that the right triangle ABC can go into the right triangle ADC, we derive that they are also the same areas. Whenever you have two triangles that can go into each other, then they must have also the same areas. So the area of triangle ABC is equal to the area of triangle ADC. But it is very easy to see from the drawing that in total the area of the triangle ADC is 20%, that is 30 square units. So I can write here that the area of triangle ADC is equal to 30 square units, and from this equation the area of triangle ABC equals to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is equal to 30 square units. From one side, but from the other side, if we define the area of this green shape, that is the area that we are looking for in this question, if we define the area of this green shape as x, that is to say, the area of this green shape equals to x square units in its size, according to our definition, then the total area of triangle ABC will be equal to x plus 5 square units. So from one side, the area of triangle ABC is also equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We derive that x plus 5 equals to 30. Here we subtract 5 from the equation and finally get that x equals to 30 minus 5, that is 25 square units. Okay, and that is the answer to the question. I'll repeat again. If we found out that the area of this green shape is equal to 25 square units. So we finish with the second question. The next step, we summarize the lecture. We start with the first question, of course. mission in this first question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. This is called AP, that is equal to 6 units in length. This is the segment BC, that is equal to 5 units in length. Again, our mission is to find out the area of this rectangle ABCD. So ABCD is a rectangle, therefore all those 4 angles inside the rectangle ABCD is equal to right angles, are equal to 90 degrees in their sizes. In the next step, we define the center of this semicircle. This point is point O, and we define the radius of this semicircle as x. Also, we define the point of tangency of tangent BC with this semicircle. This point is point M. And finally, we define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. So point O is the center of this semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x units in its length according to our definition. Likewise, OE is also the radius of the semicircle, that is equal to x. We join points O and M together by straight line. OM is of course the radius of this semicircle, that is equal to x. And because of the fact that the radius OM of this semicircle is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. By doing this construction, the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4 rectangles. In total, they must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 rectangles must be equal to 90 degrees in its size. So inside the small quadrilateral DMOA, we have 4 rectangles, and according to rule 5, any quadrilateral that has 4 rectangles must meet its rectangle equals a square. So we relate to this quadrilateral DMOA as a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DMOA, side MO equals to the opposite side DA. But MO is x, therefore DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, the opposite sides must be equal to each other. That is to say, side DA must be equal to the opposite side CB, but DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we get a peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the semicircle or circle must be equal to 90 degrees in its size. Therefore, this peripheral angle APE must be equal to 90 degrees in its size according to rule 7. In the next step, we find this angle as alpha. So in the rectangle APE, this angle equals to alpha, this angle equals to 90 degrees, therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in the triangle. Likewise, in the big triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first angle must be equal to 90 degrees minus alpha according to the sum rule that said that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we prove that the big right triangle ABC is similar to this small right triangle APE according to angle similarity rule. Why those two triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the right triangle APE, and the angle A also belongs to the big right triangle ABC. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on the circle, therefore they are equal to each other. So in total, if you found out that all the angles of the right, this big right triangle ABC are correspondingly equal to the angles of this right triangle APE, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of triangle APE over side AB of triangle ABC is equal to side AE of triangle APE over side AC of the big right triangle ABC. And again, we derive that side AP of the right triangle AP over side AB of the big right triangle ABC equals to side AE of the right triangle APE over side AC of the big right triangle ABC. AP is 6. AB is the missing side, so leave it as it is. AE is 2x, this is the diameter of the semicircle, that is 2x. And AC in total equals to 6 plus 5, this is 11. So in total, if we found out that 6 over AB equals to 2x over 11, here we first multiply this equation. And finally found out that 6 times 11 is 66 equals to 2x times AB. Here we divided this equation by 2. And finally found out that 66 over 2 is 33, so 33 equals to 2x over 2 is x. 2x over 2 is x, so in total this expression equals to x times AB. So in total we found out that 33 equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. So AB, side AB equals to 33 over x units in its side. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length is AB and the width is BC. Therefore, in total, the area of rectangle ABCD must be equal to AB times BC. But AB is 33 over x and CB is x. So total the area of rectangle ABCD equals to 33 over x times 33 over x times x. We have x in the denominator and x in the denominator, so x will get cancelled, and we left only with 33. So in total, if we found out the area of this rectangle ABCD is equal to 33 square units. Finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. Our mission in this second question is to find out the area of this main shape. So in the drawing, we have square ABCD. We know that line segment BP equals to line segment PC. This is triangle OPC is equal to 5 square units in its size. Again, our mission is to find out the area of this main shape. So we define the length of this line segment BP as A. So PC must be also equal to A because they are equal to each other. We know that all the sides of any square are equal to each other. Side BC equals to A plus A, that is 2A. Therefore, side AD must be also equal to 2A units in its length because ABCD is a square. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta because they are equal to each other. In addition, we know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and are located between the parallel lines AD and BC. This is why AD is parallel to BC. Therefore, those two alternating angles that are located between the parallel lines AD and BC must be equal to each other in their sizes, according to rule 15. So if the size of this angle is better, then the size of this angle must be also equal to beta, because they are equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallels BC and AD. Therefore, they must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha according to rule 15. In total, we shall find out that the big triangle ADO is similar to this small triangle POC according to angle similar to one. That is to say, in both triangles we have angle theta, in both triangles we have angle beta, and in both triangles we have angle alpha. Therefore, those two triangles are similar to each other according to angle similar to one. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule 22. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing, we have those two similar triangles, A, B, C, and D, E, F. And according to this rule 22, the ratio between the areas of those two triangles, that is actually the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides. So what is the square of the ratio of their corresponding sides? In those two triangles ABC and those two similar triangles ABC and DEF, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF, and finally side CB is the corresponding side of side DF. So the square of the ratio of their corresponding sides, here side AC is the similar triangle, is the corresponding side of DE. Therefore, the square of the ratio of those two corresponding sides is of course AC over DE squared. So the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. That is to say, it is AC over DE squared. Likewise, the square of the ratio of those two corresponding sides is AB over DF squared. And finally, the square of the ratio of those two corresponding sides will be equal to CB over EF squared. Okay, so the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. So we can actually implement rule 22 in our drawing. One code in our drawing. We have those two similar triangles, and according to rule 22, the ratio between the areas of those two similar triangles, that is to say, the area of triangle, the big triangle DOA over the area of the small triangle COP, is equal to the square of the ratio of their corresponding sides. Side AD is the corresponding side of side CP, and therefore the square of the ratio of those two corresponding sides is of course AD over PC squared. Is AD over PC squared. So the ratio between the areas of the two similar triangles, that is to say, it is the area of triangle DOA over the area of triangle COP, is equal to the square of the ratio of their corresponding sides. It is actually AD over PC squared. The area of triangle DOA is unknown, so really it is over the area of triangle COP. The area of this triangle COP is 5 square units, so we substitute the area of triangle COP by 5, and it is equal to AD over PC squared. AD is 2A, PC is A. Again, AD is 2A and PC is A squared. So we have squared. We have A in the denominator and A in the denominator, so A will get cancelled. So we cancel A, we have here 2 squared, that is 4. So in total, we found out that the area of the big triangle DOA over 5 equals to 4. Here we multiply this equation by 5 and finally found out that the big triangle DOA equals to 5 times 4, that is 20 square units. And with the area of this big triangle DOA is equals to 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of triangle ADO over side PC of triangle COP is equal to side AO of triangle ADO over side OC of triangle POC. Repeat again. Side AD of triangle ADO over side PC of triangle POC equals to side AO of triangle ADO over side OC of triangle POC. AD is 2A and PC is A. Again, AD is 2A and PC is A. And it is equal to AO. AO is 2B. AO is the missing side. AO or OC. AO and OC are the missing sides. So we leave them as they are. Okay, so AD. So we have A in the numerator and A in the denominator, so A will get cancelled and we left only with 2. So total we found out that 2 equals to AO over OC. Again, 2 equals to AO times 2 equals to AO over OC. Here we multiply this equation by OC and found out actually that 2 times OC equals to AO. We define the length of side OC as B and we put a substitute OC by B and we found out that AO equals to 2B. That is to say, we found out that if the length of this side OC is B, then the length of side AO is 2B. That is to say, AO is twice as long as OC. So OC is B and OA is 2B. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is rule 23. So in the drawing we have triangle ABC that could be any triangle. In this triangle ABC we do the red line segment AP. By drawing the red line segment AP, we can do two smaller triangles. Triangle ABP and triangle APC. Rule 20. This rule 23 is about those two small triangles that were created by drawing the red line AP and triangle ABC. According to this rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. So the ratio between the areas of those two triangles is the area of triangle ABP over the area of triangle APC. So that ratio is equal to the ratio of their corresponding bases. The base of triangle ABP is BP. The base of triangle APC is PC. So it is BP over CP. Again, the ratio between the areas of those two triangles, small triangles, that is to say the area of the small triangle ABP over the area of the small triangle APC equals to the ratio between their corresponding bases. That is actually BP over PC, because BP is the base of triangle ABP and PC is the base of triangle APC. The ratio is of course BP over PC. So we can implement rule 23 in our drawing. Actually, how we get to this equation, this expression, because we know that the area of triangle ABP is the base, that is BP, times the height, that is h, over 2. The area of this triangle APC is the base PC times the height, that is h. Both triangles have the same height, that is h, over 2. And the ratio between the rest of those two small triangles is the ratio between those two expressions, of course. And the ratio between those two expressions is those two. We have edge in the numerator and edge in the denominator, so edge will get cancelled. We have 1 up in the numerator and 1 up in the denominator, so 1 up also will get cancelled, and we left only with BP over PC. So in total, we found out that the ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. That is actually BP over CP. So we can actually implement rule 23 in our drawing. Because in our drawing, we have the big right triangle ADC. This is line segment OD that divides the big right triangle ADC into two parts. So all the requirements of rule 23 are satisfied, and therefore we can implement rule 23. According to rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. That is AO over OC, because AO is the base of triangle ADO and OC is the base of triangle OCD. Repeat again, according to rule 23, in this right triangle ADC, we have line segment OD that divides the triangle ADC into two parts. The ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. This is AO over OC. Repeat again, according to rule 23, the ratio between the areas of the small triangles is actually the triangle ADO over the triangle ODC. This is the ratio between the areas of the small triangles, and it is equal to the ratio between their corresponding bases. The base of triangle AOD is AO, and the base of triangle DOC is OC. So the ratio of their corresponding bases is of course AO over OC. AO over OC. So the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases, that is AO over OC. The area of triangle ADO is 20 square units, so we do the area of triangle ADO by 20 over the area of triangle DOC. The area of triangle DOC is unknown, so we left it as it is, and it is equal to AO over OC. AO is 2B and OC is B. Again, AO is 2B and OC is B. We have B in the numerator and B in the denominator, so B will get cancelled, and we left only with 2. So in total, we should find out that 20 over the area of triangle DOC equals to 2. Here we multiply this equation by the area of triangle DOC, and finally found out that the 20 equals to 2 times the area of triangle DOC. Here we divided the equation by 2, and finally found out that the area of this small triangle DOC is equal to 20 over 2, that is 10 square units. Okay. We know that ABCD is a square, so all of its sides are equal to each other. And therefore, the area of this, actually, the big right triangle ABC is converted to the big right triangle ADC according to side rule. So while those two triangles can go to each other, side AB of triangle ABC is equal to side DC of triangle ADC. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC, because ABCD is a square. And finally, side AC is the common side that belongs to both triangles, so we can write down that AC equals to itself is a common side that belongs to both triangles. So in total, we have found out that the area of triangle ABC, the triangle ABC is converted to triangle ADC according to side rule. And again, we have found out that triangle ABC can go to triangle ADC according to side rule. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. But we know that the area of this triangle ADC is 20 plus 10, that is 30 square units. So we can write that the delta LADC is 30, and from this equation the delta LADC equals to the delta LADC equals to 30. We will derive that the delta LADC is also equals to 30 square units from one side, but from the other side this LADC is equal to the delta green shape plus 5 square units. So we define this green shape as x, that is to say the of this green shape equals to x square units according to our definition. So in total the of this LADC equals to x plus 5 square units. So from the other side the delta LADC is also equals to x plus 5 square units. So, and from this equation x plus 5 equals to the delta LADC equals to 30, we will derive that x plus 5 equals to 30 square units. So we subtract 5 from this equation and find that x equals to 25 square units. That is to say the area of this green shape is equals to x is equal to 25 square units. Okay, thank you very much.